Hello, everybody. Today I will be discussing my senior thesis where I explored Phil-Julia sets of non-autonomous sequences of polynomials. So to understand non-autonomous sequences, it is important to understand what a dynamical system is. A dynamical system is a pair SF where S is a set and F is a function that maps S to itself. And because of this, we can iterate F. In a dynamical system, we start with a point in S, plug it into the function F, then plug that output back into F. And we want to observe the behavior as we do this for various points over a lot of iterates of F. Since we'll be looking at complex dynamical systems, S is taken to be the Riemann sphere, where the Riemann sphere is the complex numbers union infinity, and F is taken to be a rational function. So to better understand what a dynamical system is, here's an example. Let's take S to be the real numbers and F to be x squared. If the absolute value of x is greater than 1, then f of n of x goes to infinity, since any number with an absolute value greater than 1 gets larger every time you square it. If the absolute value of x is less than 1, then f of n of x goes to 0, and if the absolute value of x equals 1, then f of n of x is 1. The fixed points for this dynamical system are 0 and 1, and 0 is attracting since points close to 0 get closer under f, and 1 is repelling since points just above 1 get larger under f, and points just below 1 get smaller under f, so they get away from 1. Now we'll be working with complex numbers from now on and be using the Riemann sphere as a set for all of our dynamical systems. These are the definitions of the two Julia and Phil-Julia sets. For those of you who don't have a mathematical background, I'll explain what these definitions mean. The two sets are predictable, meaning that points in the two set that start close to each other stay close to each other under iterations of the function. Julia sets are chaotic, meaning that points that start close to points in the Julia set will initially have very different outcomes. All Julia sets are bounded under the function, meaning that they don't go to infinity. Now let's look at f of z equals z squared, where S is the Riemann sphere. The Julia set of f is the unit circle, which makes sense because points just above 1 get really big under f and points just below 1 get really small under f, so it's chaotic. The Phil-Julia set is the closed unit disk since those are the points that are bounded under f. On the slide is an image of the Phil-Julia set of f. So on the slide, you can see I represented a few points that were iterated over f. The iteration in red is a point on the unit circle. So since the distance from 0 is 1, when you square it, it will remain on the unit circle. The iteration of a point outside the unit circle is drawn in blue and it goes off to infinity. And the iteration of a point inside the unit circle is drawn in green and it goes to 0. For the function g of z equals z squared minus 1, the Phil-Julia set is represented on the slide and it is commonly referred to as the basilica. What is important about g is that it has a critical point at 0, which is periodic, forming a super attracting two cycle consisting of 0 and -1, since g of 0 equals -1 and g of -1 equals 0. So on the image on the slide, you can see a point inside the Phil-Julia set is represented in red and remains bounded under g, and actually eventually iterates to the two cycle consisting of 0 and -1. The point outside the Phil-Julia set is in green and it eventually goes to infinity. We just looked at the dynamics of f and g because quadratic functions are the simplest complex differentiable functions that have a degree greater than 1. So they'll be the ones that we analyze in our investigation of non-autonomous sequences of polynomials. We won't be looking at rational functions of degree 1 because those functions are already well understood. So we will now be moving on to non-autonomous iteration. In the dynamical system example earlier, we had f of x equals x squared be our function and it did not change. However, with non-autonomous sequences of polynomials, the polynomial can change with each iteration and the coefficients and degrees are bounded. The notions of the two Julia and Phil-Julia sets for autonomous sequences extend naturally to non-autonomous iteration as well. For part of my thesis, I wrote a program in Python that used the boundedness of Phil-Julia sets to graph the Phil-Julia sets for non-autonomous sequences of two polynomials of degree 2. So we will first look at f of n of g of 1 for f of z equals z squared and g of z equals z squared minus 1. On the slide, you can see the Phil-Julia set for this sequence, which is created using the program I wrote. And notice how around 0, it pinches, and all the points above and below 0 are part of the unbound of the cube component, meaning they go to infinity. So we proved in my thesis that all the points in the set denoted by the blue line in the graph are part of the unbounded component. You can see an outline of the proof, which is saying that we plugged RE to the I theta, where theta equals pi over 2 and negative pi over 2 into G, and showed that it was less than -1, so it'll get blown up under F, making it part of the unbounded 2 component. So we will now look at f of n of G of 2. On the slide, you can see the Phil-Julius set for this sequence, and notice how around 0, all the points are part of the Phil-Julius set, meaning they're bounded under the sequence. But for points around -1 and 1, it pinches, and all the points above and below those 2 points are part of the unbounded 2 component. So we proved in my thesis that all the points denoted by the blue lines in the graph are part of the unbounded 2 component. You can see an outline of the proof, which is saying that we plugged a plus bi into G for a equals 1 and a equals -1, and iterate over those sets twice, and found that the absolute value of that was greater than 1, so it'll get blown up under F. So we will now look at f of n of G of 3. On the slide, you can see the Phil-Julius set for this sequence, and notice how around 0, it pinches, and a lot of the points around 0 are part of the unbounded component. This is similar to f of n of G of 1, since for that sequence, the Phil-Julius set pinched around 0 as well. Except here, the points of the unbounded 2 component are at different angles. So we proved in my thesis that all the points in the set denoted by the blue lines in the graph are part of the unbounded 2 component. You can see an outline of the proof, which is saying that we plugged in RE to the I theta, where theta equals k pi over 4, for k equals 1, 3, 5, and 7 into G, and found that it mapped to the line a plus bi, where a equals -1 and b doesn't equal 0, which is part of A2. Now, since we are plugging in a subset of A2 into G and have 2 iterations left, by theorem 8, f of n of G of 3 goes to infinity. Now below you can see the dynamics for the sequence f of n of G of m, where m equals 4, 5, 6, and 7. As you can see, it follows the pattern we noticed earlier. For the even iterates, we can see that around 1 and -1, the Phil-Julius set gets pinched, but points around 0 are in the Phil-Julius set. However, for odd iterates, we get the opposite. This is because of the 2-cycle in G consisting of 0 and -1. If you start with a component containing -1 or 1 and do an even number of iterates, but only do a few of them, there's a good chance that you'll end up getting close to -1, but outside the unit disk. So the points close to 1 or -1 might go to infinity at first if you only do a few iterations. Now you can see that the Phil-Julius sets for f of n of G of m for m equals 8, 9, 10, and 11. Here you can see more tendrils around -1 and 1 and 0, depending if you do an odd or even number of iterates. And the more iterates you do, the closer to the basilica it becomes. Thus, if m was very large, it would approach the basilica. So we will now discuss the connectivity of Julius sets for these non-autonomous sequences. First, the definition of a critical set for a sequence is 0 and all the points that iterate to 0 under the sequence of polynomials. This definition is important because there's a theorem that says that the Julius set for a sequence is connected if and only if the critical set of the sequence is contained in the Phil-Julius set for the sequence. So in my thesis, we proved that for the functions f and g for any natural number m, the Phil-Julius set for the sequence f of n of G of m is connected. We did this by proving that the preimages of 0 under G are contained in the closed unit disk, which will make them bounded under F. We did this by showing that G of m of all the points in the critical set of G will either be 0 or -1, since all the elements in the critical set of G map to 0, and 0 was contained in the 2-cycle with -1. Thus, all the points in the critical set will either map to 0 or -1 after m iterations of G, making them all contained in the Phil-Julius set for the sequence, so that the Julius set is connected by the theorem that we just discussed. Using the same logic, you can prove that the Julius set for a sequence of the form f of n of h of m of z is disconnected if the function h of z is a polynomial with a cycle that has a point outside the unit circle. Thanks so much for watching my presentation. So here are the references that I used.